The eye sees only what the mind is prepared to comprehend. That quote from Robertson Davies, it absolutely hits the nail on the head for the crisis facing autonomous vehicles today. I mean, a self-driving car can have the absolute best cameras and LiDAR systems in the world, literally seeing every single pixel of the road. But if the car's artificial mind can't comprehend what those pixels actually mean in the real world, just seeing the road isn't going to be enough.
Welcome to today's Explainer. We're digging into some fascinating source material today to uncover a massive shift happening right now in the world of autonomous vehicles. We're finally moving past that old bottleneck of just getting cameras to work, and we're tackling the real issue, the autonomous driving reasoning crisis. We're going to see exactly how engineers are using large language models to give AI a genuine cognitive leap.
Okay, let's dive into this. Here is our roadmap for today. 1. The new driving bottleneck. 2. The cognitive hierarchy. 3. 7 core reasoning challenges. 4. Teaching cars to think. And finally, 5. The final speed trade-off.
Chapter 1. The new driving bottleneck, from sensing to understanding.
For years, the biggest hurdle in self-driving tech was perception. Could the car reliably detect a stop sign or a pedestrian in the pouring rain? But companies like Waymo and Cruise are realizing that the physical hardware is actually pretty solid now. The real bottleneck? It's reasoning. Let's put this into perspective. Imagine a ball rolls out into the middle of a neighborhood street. A basic, rule-based autonomous car just sees a rolling object. It calculates the trajectory, decides the ball itself isn't a physical threat, and might just completely ignore it, or maybe lightly tap the brakes. But a thinking car, one equipped with true reasoning, doesn't just see a ball. It uses probabilistic, context-aware reasoning to anticipate that, hey, a kid is probably chasing after that ball. It grasps the unwritten context and slows down preemptively. That is the massive difference between pure pattern matching and actual comprehension.
To pull off this thinking car, researchers are doing a total overhaul of the software architecture. They're ditching those traditional, rigid pipelines and introducing something called the cognitive core. The big idea here is that reasoning shouldn't just be some sequential module tacked on to the end of a process. Instead, engineers are building a cohesive cognitive architecture centered right around large language models and multimodal models. This core essentially acts as a central brain. It understands, coordinates, and empowers literally every single system in the vehicle, from what it sees to how it steers.
Section 2. The cognitive hierarchy. The evolution of the AI driver.
Now, to actually build that central brain, researchers break down the massive task of driving into a few manageable pieces. Notice how this framework perfectly maps out the evolution of the AI driver. Down at the bottom, we've got the sensorimotor level. Think of this as the car's basic reflexes, just direct mappings from sensors to actions, like slamming the brakes if an obstacle suddenly pops up. Moving up a step, we hit the egocentric reasoning level. This is all about following the rules, lane keeping, planning a route, reacting to other cars based strictly on data it observes. But the absolute holy grail? That's at the top, the social cognitive level. This is the ability to literally read the room. It takes social common sense, understanding complex traffic laws, and actually anticipating the unspoken intentions of human drivers and pedestrians.
Section 3. 7 core reasoning challenges. Breaking down the roadblocks.
So, current self-driving cars? They've pretty much mastered those bottom 2 levels. They've got great reflexes, they follow lanes perfectly, but they hit a massive wall at that highest level of social awareness. Take a look at this taxonomy. It breaks down the 7 distinct hurdles that are blocking level 4 autonomy and beyond. Over on the left, you've got challenges grouped under egocentric reasoning, stuff like fusing data from different sensors or dealing with AI hallucinations. But as you look to the right, under the social cognitive level, the challenges totally shift. We go from physical engineering problems to incredibly complex social problems.
Let's contrast these two to really grasp the difference. Egocentric challenges are definitely tough. Seamlessly fusing radar and camera data to make sure you don't hit a wall is no joke. But social cognitive challenges, they are exponentially harder. How in the world do you program a car to handle long-tail events? Those bizarre 1 in a million scenarios you can literally never fully train for? Or even wilder, how do you teach a machine to play the social game?
The social game. Challenge number 7. Think about what happens when you pull up to a 4-way stop at the exact same time as another driver. What do? You make that super awkward human eye contact, do the polite little head nod, maybe a subtle wave of the hand, or you kind of inch forward just a bit to show you're going. It's this completely unwritten social negotiation. So how on earth do you teach an algorithm to do that? To engage in implicit nonverbal communication? Because if a car just rigidly follows the written law, it might sit at that intersection forever, totally paralyzing traffic. It absolutely needs social intelligence.
Section 4. Teaching cars to think. Integrating LLMs. To solve these incredibly nuanced social puzzles, engineers are tapping into the massive world knowledge locked inside large language models. By integrating the same kind of models that power modern chatbots, these cars can access a deep well of common sense to decode those implicit social norms. But bringing these two worlds together creates what we call a paradigm gap. Check out this stark contrast. Autonomous driving requires strict, deterministic logic in a physical world. It needs real-time, millisecond reactions so you don't crash. LLMs, on the other hand, they're probabilistic. They're guessing the next best word based on tons of information, and they are high latency, which means they actually take time to think. Grasping this gap is absolutely crucial, because the massive engineering challenge right now is taking this brilliant but slow-thinking conversational brain and safely plugging it into a fast-moving, 2-ton physical machine.
And this beautifully illustrates why that huge effort is totally worth it. Check out the middle scenario here, a broken traffic light at a busy intersection. A traditional, brittle rule-based system sees that broken light, falls back on its hard-coded safety rules, and will probably just freeze. It's waiting for a green light that is literally never going to come. But the reasoning system, it looks at the whole context. It sees the cars on the left and right, queries the unwritten rules of right-of-way, checks its own position on the major road, and then safely and confidently navigates through the intersection. It actually reasons its way out of the problem.
Plus, this reasoning capability leads to something even more important: trust. Historically, AI in cars has been this opaque black box. The car slams on the brakes, and you have absolutely no idea why. But the new trend, thanks to these language models, is creating glass box agents. Because these models use language to process their logic, they can transparently explain their thought processes to the passenger in real time. Imagine sitting in your car and it says, "Hey, I'm slowing down because the car in the right lane is accelerating and won't let me merge." That kind of transparency is a total game changer for passenger trust.
Section 5. The final speed trade-off. Fast versus slow thinking.
So, we want our cars to be brilliant and socially aware, for sure. But we also really need them to not crash into sudden obstacles. This creates the ultimate tension, the time it takes to think deeply versus the physical need to react instantly. To solve this, engineers are borrowing a concept straight from human psychology. Think of Nobel laureate Daniel Kahneman's famous fast versus slow thinking analogy. Humans have a fast automatic reflex system and a slower deliberate reasoning system. Well, autonomous systems are adopting a dual process architecture to do the exact same thing. First, you have fast reactive controllers built purely for millisecond evasion, keeping the car safe. Second, you have the deliberative LLM brain handling the slow, complex social planning. But the real genius is the third piece, dynamic arbitration. The system has to flawlessly and seamlessly switch between these two minds, depending on the exact context of the road.
And that leaves us with this final, truly provocative question. Can we successfully build an AI that deliberates like a philosopher but reacts like a race car driver? That is the high-stakes balancing act of this new cognitive core. It's an incredibly thrilling frontier, and solving it is really the only way we're ever going to see fully autonomous vehicles mastering the complex social ballet of our city streets. I really hope this explainer helped clarify the massive cognitive leap happening right now in self-driving tech. Keep your eyes on this space, because the future of transportation isn't just about seeing better, it's about thinking smarter.